Okay, so we are now going to answer the final y in the proof of Riemann's theorem. And we already know what this y is. We need to prove that these sums converge to L as j approaches infinity. So because we want to prove a limit, so the very first step would be to choose an epsilon, because that's what we always do. So let us start by choosing a positive real number epsilon, and our starting point would be this limit, something else that we already know. Since limit of a n j, limit of this sequence as j approaches infinity is 0, that's why for this epsilon we can write something. We have some natural number j naught such that the absolute value of a n j, these terms, is less than or equal to epsilon over 2 for all natural numbers j greater than or equal to j naught. But in this statement, let us also include the fact that this epsilon over 2 is less than epsilon. Okay, so this is something we directly get from this limit. Now let us get another natural number which we are going to call j1, and that will somehow be related to the fact that both case 1 and case 2 occur infinitely many times. This is something we have already proved. So accordingly we are going to now write, since case 1 and case 2 both occur infinitely many times, there exists a natural number j1 such that j1 is greater than or equal to j naught. The sum of the terms a and j, as j varies from 0 to j1, is less than L, and the sum of the terms a and j, as j varies from 0 to j1 plus 1, is greater than or equal to L. But the question is, how are these inequalities being obtained from the fact that case 1 and case 2 both occur infinitely many times? Note that since case 1 has to occur infinitely many times, there exist infinitely many such j1s, infinitely many such upper limits of such sums, such that those sums are less than L. Okay, you get the point. Similarly, because there should be infinitely many times that case 2 occurs, so here also you will get infinitely many upper limits of such sums, infinitely many natural numbers for which all the corresponding sums are greater than or equal to L. Because of this fact that there are infinitely many such choices here and infinitely many such choices here, we can choose a natural number J1 that is so large that it not only exceeds J0, it may be equal to J0, but in general it exceeds J0, so that this also happens and this also happens. Okay. Now what do we have from these things? Then L minus epsilon. Let us start with L minus epsilon. L minus epsilon is definitely strictly less than L because epsilon is positive. But now immediately we can write this. L is less than or equal to this sum A and J, J varies from 0 to J1 plus 1, and we know that you can write this sum as this sum plus A n J1 plus 1. Okay. Now, if I write another inequality that this is less than, okay, and now first you note this. We already know that this sum is less than L. So, in its place if I write L, that means I am writing more. And then what else can I write? So this term is less than or equal to L plus this, because any real number is less than or equal to its absolute value. However, this absolute value itself is less than epsilon. But where are we getting this from, that this absolute value is less than epsilon? Remember that in the beginning we have this thing, no? A n j is less than or equal to epsilon over 2, which is less than epsilon, for all j greater than or equal to j0. Now can you choose J1 plus 1 in place of J? Yes, you can. Let's see why. J1 plus 1 is greater than J1 and J1 is greater than or equal to J0. So this choice can be made in place of J. And that's why this is justified. So now what do we get from all these things? From these things we get that, okay, let me just write. We can now rewrite these things slightly differently. L minus epsilon is strictly less than this sum, which is strictly less than L plus epsilon. And those inequalities are equivalent to this one. J1 plus 1 A n j minus L is less than epsilon. Okay. Now we are going to claim something which has this form, the form of this inequality, and which is a more general statement than this, and then we will have to prove that claim. We now claim that this here we have j1 plus 1, here I am taking something s less than L for all natural numbers s greater than or equal to j1 plus 1, and for this we are going to apply induction on s. And the base case is of course s equal to j1 plus 1, and that in that case we already have the inequality, and in fact this is what gave us the idea of having this in the first place. The base case it is s, right? S equal to j1 plus 1 has already been proved above. So now we are going to make our induction hypothesis. Assume that Anj this to S naught minus L is less than epsilon for some natural number S naught greater than or equal to j1 plus 1. Now we want to prove the same inequality, the similar inequality where we have S naught plus 1 in place of S naught. So let us now see how that can be done. Okay, so the argument now goes like this. If an S naught plus 1, if this term is less than 0, then summation of a and j, where j varies from 0 to S naught, must be greater than or equal to L, and so we have some inequalities. Let me first write the things down and then I will explain. So the chain of inequalities goes like this. L minus epsilon, we still start with L minus epsilon because we need this thing. So L minus epsilon is less than L minus epsilon over 2. This of course you understand because here we are subtracting less from L. So that's why this inequality. But now this is less than or equal to, this part is going to be a little bit confusing. L is less than or equal to this, so let's write this in place of L. A and j, where j varies from 0 to S naught. But in place of minus epsilon over 2, we are going to replace that with this A n S naught plus 1. that too with a plus sign. Why that is so, I am going to the why part afterwards. This is less than what we are writing here, L plus epsilon plus this, okay, L plus epsilon plus an s naught plus 1, and this itself is less than L plus epsilon. Okay, so let us now justify all these things. What we wrote here is that if an s naught plus 1 is a negative real number, then this is greater than or equal to L. This itself is the first question, why that is so. That's because you remember the definition of this sequence. In this sequence, we decide one term based on all the previous terms using case 1 and case 2. Now, if it were the case that this sum is less than L, right, then that fell under case 1, and so the next term, this in that sequence, would have to be chosen from A plus. And that means what? That just means that an s naught plus 1 would be non-negative. So that means if an s naught plus 1 is negative, then n s naught plus 1 could not have come from A plus. It has to come from A minus. And that happens only when we have this, because this falls under case 2. The other inequality will fall under case 1 and we will end up having this, but this is not what we have this. So that's why we are having this. Okay, now because of these things, let's see how these inequalities are coming. This one we understand, of course, but what about this one? L is already less than or equal to this, so in place of L we have written this, so we have the less than or equal to sign. But what about the other things? Is it true that we also have this inequality? Actually that is true, but how? Let's see how. This inequality is equivalent to, if you multiply on both sides by minus 1, then it becomes equivalent to this. However, because an s naught plus 1 is a negative real number, its negative is its absolute value by the definition of absolute value. And I think you can recognize where this would come from. This would come from that thing that we have in the beginning. An j is less than or equal to epsilon for all j greater than or equal to j naught. Now the question ultimately boils down to this: can we take s naught plus 1 in place of j? In other words, is s naught plus 1 greater than or equal to j naught? It is. Why? Because you see, s naught plus 1 is greater than S naught, and S naught is greater than or equal to J1 plus 1, which is greater than J1, that is greater than or equal to J0. So definitely S naught plus 1 is greater than or equal to J0, and so can be considered here, which means this inequality, and this implies this. So that is why not only is L less than or equal to this, but minus epsilon over 2 is also less than or equal to this. Okay. Now, so this much we have understood. But then after that we are writing that this is less than L plus epsilon plus A n S naught plus 1. Where is that coming from? That comes from the induction hypothesis. Because you see, this part I think I can now erase, because we have understood the previous inequalities. Now if you write this induction hypothesis, this is something we have assumed, without using absolute value, then it would look like this: L minus epsilon is less than L plus epsilon. So that means this sum is less than L plus epsilon. So if we write L plus epsilon in its place, then we are writing something more, strictly more. So that's why this is less than L plus epsilon plus A n S naught plus 1. But because this is negative, if we do not write this, then it will still increase the value. So that's why we have L plus epsilon. So this is one type of inequalities. If A n S naught is greater than A n S naught plus 1 is less than 0. Why am I saying greater than? But there is that other case also. If A n S naught plus 1, see there are many layers of suffixes, do not get confused. A n S naught plus 1 means we are adding 1 to S naught, not to this 0. Okay. Now if this is non-negative, then again doing that case 1, case 2 business, zero to S naught, in this case it would have to be the exact opposite. It has to be less than L, because then only n S naught plus 1, and this would fall under case 2. So n S naught plus 1 would then come from capital A minus. Am I saying it correctly or have I messed up? Let me just think about it. No, sorry. This would fall under case 1 because we have a sum that is less than L. So the next term should be such that the suffix is coming from A plus, so that the term that we are going to have from the series, that is a non-negative real number. Yes, it's okay. And so now also we will need one such inequality. Now before I erase this part completely, let us just see for a moment what is it that we have obtained. L minus epsilon is less than this, which is less than L plus epsilon. We should again get this in this case also. But how? So what have I written here? And so we have, again I start with L minus epsilon, and this is less than or equal to L minus epsilon plus an s naught plus 1. Note that now this is not negative, now this is non-negative, so that's why we have this inequality. And this is less than summation a and j, where j varies from 0 to s naught, plus a n s naught plus 1. Now this inequality, this step is coming directly from there. Remember that this is what our induction hypothesis is. It does not depend on these if conditions. It is something we have already assumed before starting these induction steps. So that's why this is less than, or rather this is greater than L minus epsilon. So this plus this is greater than L minus epsilon plus this. Okay. Then how does it go further than this? But this itself is less than now what I have here does not look correct. What I am writing here is that this is less than L plus a n s naught plus 1. How can that be true though? Let me just think. I've got confused about this part. Let me just think for a moment why I wrote this. Till this it's okay, but now after this what I have written is just simply this a n s naught plus 1, and then I wrote that this is less than L plus epsilon. The confusing part is this inequality. Where am I getting this from? Oh, okay. Yeah. I am getting it from here. This sum which we have here is less than L because now we are under this if condition. So that's why if I write L in place of this, then I will have this inequality, and this is already there. Okay. But what about this part? This part is also easy. You again recall your condition that we have got in the beginning of all these things. For all j greater than or equal to j naught. If I wanted, I could have written one more step, but let me show it here itself. A n s naught plus 1 is less than or equal to its own absolute value, which is less than or equal to epsilon over 2, that is less than epsilon. And again, we have already seen this once, that we can choose s naught plus 1 in place of j, because that is greater than or equal to j naught. So yes, this is also justified. So now you can see that we have got actually the same thing. Here, for example, L minus epsilon is less than, these are the important parts. L minus epsilon is less than this sum, this term which is less than L plus epsilon. What happens in this case? Here also L minus epsilon is less than, note carefully that they are the same thing. This is the sum of a and j's, sum of a and j's, where j varies from 0 to s naught, 0 to s naught, plus a n s naught plus 1, in spite of the fact that the conditions are different in these two cases, and that is less than L plus epsilon. So now we can write so in either case we have L minus epsilon less than summation a n j, where j varies from 0 to s naught, plus a n s naught plus 1, which is less than L plus epsilon. I am going to write, but let us also note here itself that this is actually equal to S naught plus 1, and that is less than L plus epsilon, i.e. writing these inequalities using absolute value, we get this. S naught plus 1 minus L is less than epsilon. So our induction hypothesis, which is one such inequality where we have S naught here in place of S naught plus 1, has led us to the conclusion that this is also true. So that means our induction is complete. Hence, by induction, we have our claim. And the claim itself tells us that we have our limit also. So just to see that once more so that we can write our final conclusion, let us write the claim again. For all S greater than or equal to this. That means for that given epsilon, we have found a stage J1 plus 1 such that from that stage onwards, the difference between such some values and L, all those differences are numerically less than epsilon. So for each such epsilon, we can find one such stage where this happens. So that's why we have our limit. This is I. We have strict inequality here, but if you want, you can write, write an equality also by writing J1 minus 1, or such a sum where I varies from 0 to J1 minus 1. Same thing. So this is equal to L, and that answers the final Y. And because of this, we have our rearranged series A and J converging to L, and this completes the proof of Riemann's theorem in all respects. Now, what did the Riemann's theorem teach us? It taught us that given any L, there is a rearrangement of our original series summation an, so that the rearranged series converges to L. Now, in the course of answering the many things we have in this section, we ended up solving many exercises actually, but still there is one more exercise left to solve, which tells us that in such situations we can also rearrange such a series so that it diverges to infinity, and also there exists a rearrangement which makes the rearranged series diverge to minus infinity. That is the content of the last exercise, which however we will not solve today. We will solve it next Sunday. So I am going to stop the video here itself. The next upload is this coming Tuesday, of course, and on Tuesday let's just go back to calculus. We will do field theory after that, that is next Friday. So see you this Tuesday with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.